Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay, so today I'm going to discuss nuclear physics. Okay, it's a Sunday special class. Okay, and also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. And also guys, please share my lecture details to your friends so that they will also be able to watch my free live lectures and will be benefited by it. Okay, so let's get started. Nuclear physics, I'm going to start. Okay, so nuclear physics. Nuclear physics. Okay. Okay. Meanwhile, just let me check whether I'm audible or not. Then I'll proceed further. Let's get started. Yes, I'm audible, so I'm going to proceed further. Well, so in nuclear physics, we'll start with proton. Okay. Proton, we know that proton is denoted as like this 1p1, right? One is this is 1p1. Okay. So this one denotes the mass number and this one denotes the charge number. Okay, charge number. Okay, now if you talk about electrons, electron is denoted like this, electron. Okay, electron, this is denoted by -1e0. Okay, so 0, this is the mass number and this is the -1, right? -1, charge is -1. And similarly Newton, if you talk about Newton, that is denoted by 0 and 1, 0 and 1. Okay, 0 and 1. Zero and 1. Okay, so and also so what are isotopes, guys? Isotopes isotopes are those element whose z is same, guys. Z is same means atomic number is same. Okay, that is atomic number. So z is same. Okay, and a is different, atomic mass is different. Okay, so isotopes are those elements whose z is same, atomic number is same, but the atomic mass is different. Okay, there's a quality for isotopes having same chemical property. Okay, so they have same chemical property. Isotopes having same chemical properties. Okay, next is isobars. So they have they have z, atomic number is different. We have already studied in class 11 12, guys. Okay, so z means that atomic number is for isobar atomic number is different, but atomic mass is same. Okay, a is same, a is atomic mass. Okay, so these are called the isobars. Isobars means having same atomic number but different, having same atomic mass, atomic mass number but different atomic number. Okay, and the property of these isobars are isobars having same physical property, guys. Okay, same physical, so same physical property. So isobars have same physical property. Okay, same physical property. Okay, very important point. Isotopes having same chemical property and isobars having same physical property. Okay, next is isotones. 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 Okay, isotones means same number of, this is that same number of newtons. Okay, isotones means same number of the elements having same number of, okay, same number of newtons, same number of newtons, same number of newtons, that is a minus z. Okay, n equal a minus z equal to n, that is same number of newtons. Okay, so isotones are those elements uh, for which the they have the same Newton number. Okay, so they have the same newtons. Okay, and is same for the elements called isotones. Okay, next is mirror nuclei. Mirror nuclei. Mirror nuclei. Mirror nuclei, or we can call it this iso isodiaphers. Okay, isodiaphers. 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 Mirror nuclei oblique isodiaphers. Okay, so they have same difference in number of neutron and proton. Okay, same difference, same difference in same difference in newtons number of newtons and protons. Okay, so mirror nuclei means mirror nuclei, or they are called isodiaphers. They have same difference in number of newtons and protons. So the difference between number of newtons and proton is same. Okay, these are called mirror nuclei or isodiaphers. Next is important thing, that is size of nucleus. These are basic things, guys. Okay, size of nucleus. Size of nucleus. Size of nucleus. Okay, so size of nucleus means volume of nucleus. Volume of nucleus. Volume of nucleus is proportional to number of nuclei in it. Okay, number of nuclei in it, very important. So volume of nucleus is proportional to number of nuclei in it. Okay, so number of nuclei in it means the volume, that is V, is proportional to A, that is atomic mass number, right? Number of nucleons in it, yeah, that is atomic mass number. And from here we know the volume, that is 4 by 3 pi r cube, that is going to be proportional to A. And from here we can get R is proportional to e to the power 1 by 3. This is very important result, guys. Okay, R is proportional, that means the size of this radius of nucleus is proportional to a to the power 1 by 3 is atomic mass number, okay, or number of nucleons. Here, nucleon does not have any, this you need to understand, nucleus doesn't have any sharp boundary, okay. So nucleus doesn't have any sharp boundary, but very important point, guys, but it is highly dense. It is highly dense in the sphere of radius capital R, okay. So nucleus doesn't have any sharp boundary, but it is highly dense, okay, highly dense in the sphere of radius R, okay. So we'll define that density of nucleus, okay. So rho R, this is density of nucleus, is high, very high, okay, high when R is less equal to capital R, okay, and this is low when R is greater equal to capital R, okay. So this is important point, okay. So nucleus doesn't have any sharp boundary, but it is highly dense in the sphere of radius R, okay. So like this is sphere, at this point is highly dense, and after that it is not, it is the density is low, right. So or we can write like this, PR, say this is rho R, okay, density of nucleus, rho R, that is we can write P naught, which is constant P naught, which is constant when R is less equal to capital R, that is radius of that nucleus, okay, sphere, and this is 0 when R is greater than capital R, okay. So this is the density of the nucleus, guys, okay, because at the nucleus is very dense at the sphere of radius R, okay. So from here, since we know here R is proportional to a to the power 1 by 3, or we can write R is equal to R naught a to the power 1 by 3. R naught is constant, okay. This is important result. R is equal to R naught a to the power 1 by 3, okay, where R naught value is 1.2 for me, 1.2 for me, okay, or we can write 1.2 into 10 to the power minus 15 for me, okay, very important thing. Now we'll find number density, okay, number density equal to, that is number of nucleons, number density means number of nucleons upon volume, okay, number of nucleon upon volume. So that is going to be, number of nucleon means that is atomic number, right, atomic mass number, right, a upon volume, we know that is 4 by 3 pi r cube, okay, or we can write 3a upon 4 pi r cube, and r cube value we know here, this one, r value is r naught a to the power 1 by 3, so we'll put the value. So this is going to be 3a into 4 pi, r cube is going to be r naught cube and then a, right, because a to the power 1 by 3 to 1 by 3 to the power 3 means a will get cancelled, right. This is number density, and number density is going to be, and we'll put the value of this. Okay, so number density, so number density number number density number density is going to be equal to this one, 3 into 4 pi 4 pi into r cube. R cube value we know, right? This r cube, r naught cube value, this is 1.2 for me, right? 1.2 to the for me to the power 3. Okay, so this is going to be, and if you calculate it, this is going to be almost equal to 10 to the power 44 44 per meter cube. Okay, nucleon per meter cube, or we can write like this, 20 to the power 44 nucleon per meter cube. Okay, this is very important result, guys, number density. So this can be asked, guys, in the examination. Okay, so number density for nucleus is 10 to the, that is almost equal to 10 to the power 44 nucleon per meter cube. In 1 meter cube there are 10 to the power 44 nucleons are there. Okay, that is the number density, guys, very important thing. Next is mass density, guys. Okay, these are very important thing, mass density. Next is mass density. There is different. Okay, mass density is different and number density is different, guys. Mass density means that is mass upon volume. Okay, mass upon volume, and number density means number of nucleon upon volume. Okay, so mass density, the mass density is mass upon volume, and so that is going to be mass. So this is number density, right? So this is 10 to the power 44 electrons in 1 meter cube region, right? So here this is going to be that the mass of one nucleon we know, that is 1.6 into 10 to the power minus 27, right? Into that number density we know. So number of nucleon in per meter cube. So in per meter cube, that is 10 to the power 44. Okay, so this value is going to be 10 to the power 17 kg per meter cube. So this is the mass density, guys. These two values are very important value. You need to note down and memorize it, guys. Okay, so number density for nucleus is 10 to the power 44 nucleon per meter cube. Okay, and mass density is almost equal to 10 to the power 7 kg per meter cube. Means in 1 meter cube, 7 that there are mass density means 10 to the power 17 kg per meter cube. Okay, that is 17 kg per meter in 1 meter cube, that is 17 kg. So that is the mass density, guys. These two values are important, and mass density is also called nuclear density. Okay, I'll solve one question, then it will be more clearer to you. Okay, so here we can make like this. Okay, so this is mass density means like this. This is a box of 1 meter cube. Okay, the volume of this box is 1 meter cube. Okay, so for so in this box there will be 10 to the power 44 nucleons. Okay, and the mass density or nuclear density of this volume will be 10 to the power 17 kg per meter cube, right? This 17 kg, this 17 kg, right? And 10 to the power and in this because it's a volume of 1 meter cube, right? So here the number of nucleon will be 10 to the power 44, and the mass of this box will be 10 to the power 17 kg. Okay, since V is 1 meter cube for this. Okay, now I'm going to solve one question, important question. Okay, question is, this is if earth density if earth density is equal to is earth density is equal to nuclear density nuclear density earth density is equal to nuclear density, means earth density is equal to mass density of nucleus. Okay, that is nuclear density, mass density of nucleus, right? The earth density is equal to nuclear density or mass density of nucleus. Then what will be the radius of earth what will be the radius of earth? Okay, this is the question. Okay, so if earth density is equal to nuclear density or mass density of nucleus, right, then what will be the radius of earth? That we need to find out. Okay, since we know mass of earth, we know, right, mass of earth is equal to 6 into 10 to the power 24 kg. So that is the mass, right? And now density of earth is going to be mass upon volume, right? And density of earth is going to be, that is mass is 6 into 10 to the power 24 kg upon volume of earth is going to be 4 by 3 pi r cube, right? We need to find the we need to find the radius of earth, right, r. And now in question it is given this earth density is equal to nuclear density, right? Nuclear density means nuclear density, right? This is since earth density is equal to nuclear density, or we can write mass density of nucleus, right? And that you need to, I told you, you need to remember that, memorize it, right? This we know. So earth density is nuclear density or mass density of nucleus, right? That is almost equal to 10 to the power 17 kg per meter cube, right? I told you, you need to note down and memorize it, right? If you don't know this value, you would not be able to solve this question, right? Okay, so earth density in question given, right? Earth density equal to nuclear density, and nuclear density we know, that is nuclear density is mass density of the nucleus, right? So this is 10 to the power 17 kg. Now we'll put the value. So 10 to the power 17 kg is or 10 to the power 17 is going to be 10 to the power 17 is going to be equal to this one, 6 into 10 to the power 24 upon 4 by 3 pi r cube, right? From here we can find the value of r. So value of r is going to be, so from here value of r is going to be, you can calculate it, that is going to be almost equal to 243 meter. 243 meter. Just simple, you just need to put the value of pi and this value and r cube, right, and r cube, and then you will find the value of r, and that value is going to, you can calculate it by calculator. So this value is going to be almost equal to 243 meter. Okay, this is the answer. So guys, so these two values are very important, the number density of nucleus and mass density of nucleus, or we can say nuclear density. Mass density or density of nucleus means nuclear density, right? This one important. Next next is mean square radius we are going to find. Okay, mean square radius, mean square radius, mean square radius. Okay, mean square radius. So that is what we have to find. Mean square radius means average of r square, right? Mean square radius. So here we have defined this density of nucleus, right? Rho r, that is equal to rho naught if r is less than equal to capital R, that is radius of sphere. Okay, and that value is 0 if r is greater than r, right? This one. So now we'll find this one. So r square, that mean square radius, r square average, right? Square of r square average. So that is going to be by the formula integration r square rho r d tau upon integration rho r d tau. Okay, rho r d tau. This is important formula, guys. Okay, for r square, you need to note down. R square equal to the mean square value is, or average of r square equal to integration r square rho r d tau upon rho r d tau. Okay, so we can easily find out now. Very simple. So this is going to be d tau value, will put it. Okay, so this is going to be r square is, this value is going to be this one, integration 0 to 2 pi integration, because this integration is minus infinity to plus infinity, right? And then d tau is there, 0 to pi, and integration 0 to r rho naught, because rho value is rho naught, right? Rho naught when r is less than equal to r, right? 0 to r rho, and tau value is going to be, that we know, right? Sine square, we have converted in spherical coordinate, right? So sine square, my apologies, it's r square sine theta, r square sine theta d theta d phi and dr, right? Since d tau value in spherical coordinate, r square sine theta d theta d phi and dr. Okay, important one. Okay, right? So now to find the value, so this is going to be r square equal to, this value will put it, okay, this is going to be upon 0 to 2 pi, 0 to pi spherical coordinate, guys. I have explained that in mathematical physics. R rho naught sine theta, this is r square is also there, right? Rho naught sine r square rho naught is constant, this will come outside and get cancelled. Okay, so rho r square sine theta d theta d phi and d r. Now we'll solve it. So value of r square is going to be this one. This will be 4 pi, this value, right? 0 to pi d theta is 2 pi, and 0 to pi, 0 to 2 pi d phi is 2 pi, and 0 to pi sine theta d theta is 2. So 4 pi rho naught upon 4 pi rho naught, simple calculation, rho naught, and this is going to be, this value is going to be integration 0 to r to the power 4 dr upon integration 0 to r, this is r square dr. This will get cancelled. So value of r square is going to be this one, mean square of r, mean square of radius, right? R square, this value is going to be, this one will integrate it, right? So this is going to be r to the power 5 upon 5 upon r to the power 3 upon 3, or this value will be 3 by 5 r square. Okay, so mean square value is 3 by 5 r square. So this is important. Okay, okay, so this is 3 by 5 r square. So mean square radius is this. Next, guys, next question we are going to solve. Question that is if nuclear density for hydrogen atom, if nuclear density for hydrogen atom is given by rho r equal to rho naught e to the power minus r upon a. Okay, find mean square radius. Okay, find mean square radius. Find mean square radius. Find mean square radius. Okay, this is the question, guys. If nuclear density for hydrogen atom is given by rho r equal to rho naught e to the power minus r upon a, find the mean square radius. Okay, mean square radius you need to find out, that is r square. Very simple, guys. What we will do is simply, that is simple, as we have done this. Okay, so this is going to, I'm going to write directly. So this is, I'm going to write this 4 pi 0 to r. Okay, or 0 to infinity it will be. Okay, so I'll write it. So this is going to be that mean square radius is going to be integration rho naught e to the power minus r upon a upon integration e to the power minus r upon a. This is r square is also there, right? And rho naught e to the power r minus a. This is d tau, and this is d tau. Again, we'll put the value, right? So this is going to be, so we'll put the value, and as we have done like this, right? And similarly, these values will get cancelled directly. This value will remain, right? So similarly, I'm going to do here directly. So this is going to be integration. This 4 pi will get cancelled. Rho will get cancelled. I'm going to write directly. So this is 4 pi rho naught upon 4 pi rho naught. This is going to get cancelled, and this is going to be 0 to infinity. Okay, nuclear density is 0 to infinity. R square e to the power minus r upon a upon 0 to infinity. This is r to the power 4 it will be, right? R, because d tau is r, so this is going to be r to the power 4, r to the power 4, and this is r square e to the power minus r upon a dr and dr. Okay, nuclear density of H atom is given, guys. Okay, so that and radius of this will be between 0 to infinity. Okay, well, now very simple. So this will get cancelled. Okay, this, and now r square is going to be, r square value is going to be this one, integration 0 to infinity r to the power 4 e to the power minus r upon a dr upon, so this is for hydrogen atom, nuclear density for hydrogen atom we are finding. Okay, so this is 0 to infinity, 0 to infinity r square e to the power minus r upon a. Okay, so we have a formula, guys. I have already explained it in my mathematical physics. If we have 0 to infinity, x to the power n e to the power minus minus, or we can write like this, x to the power m x to the power m e to the power minus alpha x to the power n dx. If we have this formula, this will be 1 upon n gamma m plus 1 upon n upon alpha to the power m plus 1 upon n. Okay, so this is very important formula, guys. Okay, so 0 to infinity, x to the power m e to the power minus alpha x to the power n dx is 1 upon n gamma m plus 1 upon n alpha m plus 1 upon n. Here r to the power 4, 4 is m equal to 4 here, and r to the power r upon a means r to the power 1, right? So we'll directly write the formula using this formula. So this is going to be this one, 1 by 1, because r to the power 1 here, r power is 1, right? 1 by 1 gamma m is this, m plus 1 upon 1 upon alpha is this 1 upon a, 1 upon a to the power m plus 1, right? M is 4 here, so 4, this is 4 plus 1 upon 1 upon, this value is same, gamma here, r to the 2, right? 1 plus 1, 1 upon 1, 2 plus 1 upon 2 plus 1 upon gamma 2 plus 1 2 plus 1 upon 1, right? Gamma 2 plus 1 upon 1 upon, this value is going to be upon 1 upon a to the power 2 plus 1 upon 1. So this value is going to be, right? So this value is going to be, if you write it, so this is gamma 5 upon 1 upon a to the power 5 upon gamma 3 upon 1 upon a to the power 3. Okay, this is the one. So now we know that gamma value, right? We know here this one, gamma n plus 1 equal to n gamma n. So we'll use this formula here. Okay, so if you use this formula, so this is going to be next page. This is going to be r square value is going to be this one, right? Gamma 5 value will be, we'll use it. So this is going to be gamma 5 value is 4 into 3 into gamma 3 upon 1 upon a to the power 5 upon gamma 3 1 upon a to the power 3, right? Because gamma 3 we know here like gamma 5 we can write is, right, gamma 4 plus 1, right? So by this property, gamma n plus 1 equal to n gamma n, right? So this is going to be 4 gamma n, 4 gamma 4, again gamma 4 into gamma 4 we can write gamma 3 plus 1, again this is going to be 4 into 3 gamma 3, right? This is how we've got gamma 5 value, right? This one. So 12. So this gamma will get cancelled, and this value is going to be 12a square. Okay, 12a square. So this is the r square value, that is mean square value for nuclear density for hydrogen atom. Okay, so this is nuclear density for hydrogen atom. Nuclear density for hydrogen atom. Okay. Next question. Next is experimental density, guys. Experimentally, what is the density of nucleus? Okay, very important. Experimental density. Experimental density rho r, that is equal to rho naught upon 1 plus e to the power r minus capital R upon z. R minus capital R upon z. R minus capital R upon z. Very important. This is the experimentally found density of nucleus. Okay, so rho naught upon 1 plus e to the power r minus r upon z. R minus r upon z. Okay, so in case let r equal to r, in that case PR is rho r is going to be P naught by 2, because the e to the power 0 equal to 1, 1 plus 1 2, rho naught by 2. Okay, then if r equal to r, then rho r is value of rho r is going to be rho naught by 2. Okay, and here z value is going to be t by 4.4, where value of t is r1 minus r2. Okay, I'll make a graph, then it will clear your doubt. So here, if we draw the graph, between r and rho r, this graph is going to be like this. Okay, like this. This graph is going to be like this. So from here, this one. This is value of r, this is r1, and this is r1, this is r1, and this is r2. Okay, and this value is 0.1, this is rho naught by 2, and this is 0.99 rho, 0.99 rho naught. Okay, 0.99 rho naught, this value. Okay, so here this one. Okay, this is the graph between rho r and r. Okay, this is r1 and r2. Okay, when r equal to small r equal to r, then this value is this. So here from here the value of z equal to t upon 4.4. Okay, or t equal to this. So here value of z equal to r2 minus r1 upon 4.4. Okay, so this is the graph, and experimentally the value is very important. Experimentally the density of nucleus is this rho r equal to rho naught upon 1 plus e to the power r minus r upon z. Okay, and this is the r, this is rho, right? This is the graph, and value of z equal to r2 minus r1 upon 4.4. Okay, next. Next, I'm going to discuss nuclear forces. Okay, nuclear forces. Nuclear forces. Nuclear forces. So we don't have any exact representation of nuclear force, right? But 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 we have studied the nucleus, right? And got these points. I'll write those points, but here I would also would like to write that we don't have any exact representation for nuclear force. Okay, we don't have any exact representation representation we don't have we don't have any exact representation of nuclear forces. Okay, so the points are for nuclear forces. First is strong forces. So they are strong forces, guys. Nuclear forces are strong forces. By studying the properties of nucleus, we have found it. Okay, so strong forces. Strong forces. Okay, strong forces means like there is a repulsive force. There is repulsive force. There is repulsive force between protons inside the nucleus. Okay, so because nucleus is made of proton and neutron, right? So there is a repulsive, obviously repulsive force between the proton inside the nucleus, because proton have plus charge, right? Nuclear force, okay, that is F proportional to 1 upon r square, right? That is the nuclear force, that is electromagnetic force, right? Or if r decreases, implies F nuclear force increases, right? And this is electromagnetic force. We are talking about electromagnetic force. Okay, okay, now so there is repulsive force between the protons inside the nucleus. Okay, inside the nucleus protons are, but we have seen inside the nucleus, inside the nucleus protons are found in bound state, right? We have seen the inside the nucleus protons are found in bound state, right? So it means nuclear forces nuclear forces forces are strong in nature, strong in nature. So nuclear forces are very strong compared to electromagnetic forces, right? In the nucleus, that's why they have bounded the nucleons in the nucleus, right? So nuclear forces are strong in nature. Okay, so they are strong forces. Next is attractive. So obviously, so they are, nuclear forces are attractive forces. Okay, attractive forces, they are attractive forces. So as nucleus as nucleus are in bound state, as nucleus are in bound state, as nucleus are in bound state, means nucleon, or as nucleus is in bound state, as nucleus is in bound state. So that means that is because of nuclear forces are attractive in nature, right? That's why a nucleus is in the bound state, right? So nuclear forces are attractive in nature. Next is short range forces. Okay, so they are short range forces. Short range. So short range forces. Their range is short range forces. Range is 10 to the power minus 15 meter. The range is 10 to the power 15 meter. Very less, right? Ten to the power minus 15 meter. Next is charge independent. Okay, these forces are charge independent. Charge independent. So these forces are charge independent. Nuclear forces are charge independent. So it will be between neutron neutron. It will be between proton neutron and neutron proton. Okay, and this will be attractive. This will be attractive. Okay, now spin and isospin dependent. Okay, fifth point are they are spin and isospin, spin and isospin dependent. Spin and isospin, spin and isospin dependent. Okay, spin and isospin dependent. Next is, so they have saturation property, guys. Okay, sixth property, saturation property. Saturation properties. Okay, so due to short range force, due to short range force, the force will be applicable to its neighbors. Force will be applicable to its neighbors. Okay, or to its neighboring nucleons. Okay, to its neighboring nucleons. Okay, so for heavy nucleus, saturation will occur. Okay, so due to short range force, the force will be applicable to its neighboring nucleons. Okay, and so for heavy nucleus, saturation will occur, guys. Okay, because they are short range forces. Okay, so this is the saturation property. Next is property number 7. They are non-central force in nature. Okay, non-central in nature. non-central in nature. Okay, and q, if q, that q value is 0, that means spherically symmetric. Okay, so they are spherically symmetric. Spherically symmetric. Okay, this is q equal to 0. Okay, next is q greater equal to 0. If q is greater equal to 0, value of q is greater than 0, then they are prolate values. Okay, prolate. And if q less equal to 0, then they are, that implies they are oblate. Oblate. Okay, spherically symmetric means spherical. Prolate means like this. This one. Talk about like this. This is prolate, and this is oblate is like this. Okay, this is oblate, prolate, and spherical symmetric. Okay, this is 7th property. Property number 8 for nuclear forces. Okay, velocity independent. Okay, so they are velocity independent. Velocity independent. So they doesn't they don't depend on velocity. Velocity dependent. My apology. They are velocity. Nuclear forces are velocity dependent. Velocity dependent. Okay, and 9th property is they have tensor property. Okay, tensor property. Tensor property. Okay, or I'll give example, like if we talk about tensor property, that is spin orientation dependency. Okay, spin orientation spin orientation dependency. Okay, spin orientation dependency means like if these are a spin, or if this is this spin, or if this is this spin. Okay, so nuclear forces are nuclear forces have tensor property. Okay, we know what is tensor property, right? Like if we talk about scalar means scalar have only magnitude, right? If we talk about vector, then this is magnitude plus direction. Magnitude plus direction, right? Like F force, if we talk about force, that is Fxi plus Fji plus Fz, Fyi, Fy, Fxi cap plus Fyj cap plus Fz k cap, right? So if we talk about tensor, that is going to be like a matrix A11, A12, A21, A22. That is 2 cross 2, right? So Fx is going to be like Fx has 3 components. Fxy, Fyx, Fyz, and Fxz. Fxz. Okay, so Fx has 3 more components: Fxy, Fxy, Fyz, Fxz. Okay, right? So nuclear forces have tensor property. Okay, so this is about the nuclear forces, guys. Next point is and here we know that range is proportional to 1 upon mass for nucleus. Okay, so for nucleus, this is the nucleus, guys. Okay, suppose there is one proton, okay, so there would be repulsive force F1 and F2. Okay, F1 and F2, this is Coulomb force, right? So for nucleus to be stable, for nucleus to be stable, electrostatic force between proton, the electrostatic force between protons should be balanced by nuclear force. Okay, nuclear forces. Okay, if it is not balanced, then that the nucleus is going to be unstable. Okay, next is effect of nuclear size on its stability. Okay, very important. Effect of nuclear size on its stability. Okay, so effect of nuclear size on its stability, guys. Okay, so electrostatic forces are having large range. Okay, but nuclear forces are having short range. Okay, so effect of nuclear size, what will be if size is greater or less, then what effect will be on the its stability. Okay, so electrostatic forces are having large range. So electrostatic forces have large range, but nuclear forces have short range, right? Short range. If size of nucleus increases, if size of nucleus uh, increases, the electrostatic force electrostatic force dominates because nuclear forces are short range forces, right? And nucleus becomes unstable, and nucleus becomes unstable. Becomes unstable. Okay, but if number of neutron uh, is greater than number of proton then nucleus is stable. Then nucleus is stable. Okay, so this is the effect of nuclear size on its stability. Okay, so if the size of nucleus will be larger, right, in that case electrostatic force will dominate the nuclear forces, because nuclear forces are short range forces, electrostatic forces are long range forces, right? But if the number of neutrons will be more than number of proton in nucleus, right, then the nucleus is going to be stable. Okay. Okay, next point. Next point is binding energy, guys. Okay, very important. Binding energy. Binding energy. So potential energy of system that will be negative, right, means attractive. If potential energy of system is negative, means that is attractive, right? Potential energy that is attractive. Okay, so now the definition of binding energy is the total energy the total the total energy required to be supplied to be supplied to be supplied total energy required to be supplied to a nucleus to a nucleus to a nucleus total energy required to be supplied to a nucleus to break it into its free nucleon free its free nucleon free nucleons is called binding energy. Okay, so the total energy required to be supplied required to break the nucleus into its free nucleons is called binding energy. Okay, and in equation we can explain like this. Okay, so next like this, xza plus b binding energy, that is equal to z proton plus a minus z. Okay, so this is the nucleus. So binding energy we have used, right, and it breaks into z proton and a minus z neutron, right? This is the one. Or we can write here m, which is az, right, mass of nucleus, is going to be equal to mp zmp mass of proton plus a minus z mn minus be binding energy, and divided by c square. We have converted this into mega electron volt, right? So now binding energy is going to be binding energy of this process is going to be very important formula I'm writing. ZMP, okay, number of proton, right? The mass of proton, Z into mass of proton, atomic number into mass of proton, plus A minus Z, okay, that is Newton number, okay, A minus Z, Mn, mass of Newton, minus M, Az, mass of nucleus, into C square, into C square, okay. So this is binding energy, okay, ZMP plus A minus Z Mn minus M Az into C square, okay. So this is mass of proton, mass of neutron, and mass of nucleus, okay. Very important formula, guys, you need to note down, okay. So this one, this is important formula for binding energy. Next we can write the binding energy also can be written as binding energy, that is delta M C square, okay, delta M C square. Delta M C square, okay. This is delta M is known as mass defect, where delta M is equal to mass defect, mass defect, mass defect, okay. Or BE, that is binding energy, is going to be equal to this one, delta M C square, right? Or we can convert this into delta M into C square, right? We are going to convert it into mega electron volt, right? So what we are going to do is we'll multiply by 931.5, 931.5 MeV upon C square, okay. This is the one, and this is C square is also there, right? M C square into this C square will get cancelled, right? So B is going to be, binding energy is going to be delta M into 931.5 MeV, okay. So this is the binding energy, guys. B is equal to delta M into 931.5 MeV, okay. So this is the binding energy in mega electron volt, okay. Or delta M, or we can write delta M value is, this is also important, ZMP plus A minus Z Mn minus M A Z, okay. This one, very important, delta M value, okay. ZMP, mass of proton, mass of neutron, and mass of nucleus, okay. Z is number of proton, or yeah, and A minus Z is number of neutron or atomic number Z, right? Important thing. Now mass equivalence, energy mass equivalence, okay. Mass energy equivalence, mass energy equivalence, mass energy equivalence, okay. Mass energy equivalence means like delta M, that is equal to 1 MAU, right? 1 AMU, that is AMU is atomic mass unit, right? Atomic mass unit, okay. So delta M equal to, if we take delta M equal to 1 AMU, so delta E is, we know, delta M C square, right? And delta E we have taken 1 AMU, so 1 AMU is going to be, this is mass energy equivalence, okay. 1 MU is going to be 1.6 into 1.65, 1 AMU is 1.65 into 10 to the power minus 27 kg. So this is 1 MU. Okay, 1 MU equal to 1.65 into 10 to the power minus 27 kg. Okay, so delta E's value is going to be 3 into 10 to the power 8 whole square c square, right, into delta m. This 1 point delta m value we have taken 1.6 into 10 to the power minus 27 upon will divided by 1.6 into 10 to the power minus 19. Okay, so delta E value is going to be, if we calculate it, this value is going to be 931.5 MeV. So mass energy equivalence is this. Okay, so delta E equal to 931 if delta m equal to 1 AMU, atomic mass unit, then delta E value is 931.5 MeV. Okay, next is this is Q value, right? Q value. Next is Q value. Next is Q value. Q value, what is Q value? That is the energy. Q value is the energy transferred in any nuclear, energy transferred in any nuclear reaction. Okay, in any nuclear reaction, is known as Q value. Okay, very important. So this means the energy transferred in any nuclear reaction. Okay, in any nuclear reaction, the energy which is transferred is known as Q value. Okay, in any nuclear reaction, that is Q value, guys. So I'll give example. So for, if we take any example, that is X plus X ZA into Y plus Y. Okay, so this is X is projectile, and this is parent nucleus, okay, and this is daughter nucleus, and this is ejectate, right? Ejectate. So this is the equation. Okay, so this is X projectile, and this is parent nucleus, this is daughter nuclei, and this is ejectate, right? So Q value is going to be very important formula. I'm going to write Q value. So energy transferred in nuclear reaction is Q value, right? Q value. This is going to be Q value. I'll write directly Q. Okay, Q value. So Q is going to be equal to, this is very important, mass of reactant minus mass of product into C square. Very important formula, guys, this one. Okay, Q value equal to this. Q value is this, mass of reactant minus mass of product into C square. Okay, so this means I'll write it, Q is going to be mx, this one, right, mx plus capital Mx minus capital My minus small my c square. Okay, so this is reaction, right? This is small y, this is capital Y, right? So small mx plus capital X minus capital My minus small y c square, right? Mass of reactant minus mass of product. This is mass of reactant minus mass of product. Okay, very important. Reactant minus product. And it has two more formulas which I am going to write. Q value is, this is binding energy of product. This is, I'll write binding energy in short. Okay, B of product, B of product, BE of product minus binding energy of reactant. This is reactant. Okay, you need to understand, don't get confused. This is mass of reactant minus mass of product into c square. But if we talk about in terms of binding energy, Q value is binding energy of product minus binding energy of reactant, product minus reactant. Okay, or with another formula is kinetic energy of product, minus kinetic energy of reactant. Kinetic energy of reactant. Okay, binding energy of product minus binding energy of reactant, that is Q value, and Q value is also kinetic energy of product minus kinetic energy of reactant. Okay, this one. Okay guys, just give me one minute guys. Okay, some got urgent work. Okay guys, so I'll start. So this is these are Q values guys. Okay, next is okay. So if you talk about exothermic process, okay, exothermic in case of exothermic, Q is greater than 0 guys. Okay, Q is greater than 0 means energy is released. Okay, energy is released. Okay, or endothermic reaction, endothermic in case of endothermic reaction, Q is less than 0, that is, it means energy absorption. Okay, energy absorption. Okay, so for Q greater or equal to 0, energy is released. For endothermic, that is Q less than 0, energy this is energy absorption, or energy is absorbed. Okay, these are values. Q is greater than 0 means exothermic reaction, energy is released. If Q less than equal to 0, endothermic reaction, energy is absorbed. Okay, energy absorption. Now, there's a question which is asked in TIFR, which I'm going to solve. Okay, I'll solve in next page. Question is asked in TIFR. Okay, TIFR. FR 2017. Question is, this is the curve given, okay, this curve. This is the curve, okay. This is the curve. This is 120, this is 240, this is atomic mass number, okay, and this is binding energy per nucleon, B per nucleon, okay, and this value is 8.8 8.85 8.85 mega electron volt, and this value is 7.5 mega electron volt, 7.5 MeV, okay, this one, and this is 120, this is 240, and this is binding energy per nucleon, okay, and these are atomic mass number, okay. This is the question, and in question it is written, if nucleus mass of 240, if nucleus of mass 240 breaks into 2 equal nuclei, okay, then energy released or absorbed is, okay. So if nucleus of mass 240 breaks into 2 equal nuclei, okay, it breaks into 2 equal nuclei, okay, then energy released or absorbed is, we need to find energy released or absorbed, okay. So, and this is explained by graph, okay. Now options are given. Option A is 240 MeV, option B is minus 240 MeV, option C is 120 MeV, and option D is minus 120 MeV, okay. So this is the question, guys. This is the graph given. This is binding energy per nucleon, and these are the nucleus, okay. This is the nucleus. So if nucleus of mass 240, this breaks into equal nuclei, okay, equal nuclei of mass this 120, okay, equal nuclei means this is given in the equation, this graph, okay, 120, right. Then energy released or absorbed we need to find. Energy released or absorbed means we need to find Q value, right. So now I'll solve it. So we have been given mass A breaks into mass B plus mass B, okay. The mass number for it 240, mass number for it 120, right, and binding energy per nucleon for this 241, right, for 241 is 7.5, for this binding energy is 8.5, okay, this one 8, for 120 corresponding 120 binding energy per nucleon is 8.25, right, for 240 corresponding binding energy is 7.5, right, this one, this is binding energy, this is atomic mass, right. 7.5. Okay. So we'll find Q value. I have explained three formulas right here, three formulas. So we'll use one formula, that is binding energy formula. So this is Q value is binding energy of product. Q value is binding energy of product minus binding energy of reactant, right? This is the binding energy of product minus binding energy of reactant. So product is this, there are two products, right? So binding energy, this is binding energy per nucleon. For one nucleon, binding energy is this. For 120 nucleon, this is going to be 120 into 8.5 plus there are two atoms, right? So 120 into 8.5 minus this one 240 binding energy per nucleon. There are 240 into 7.5, right? And we'll solve it very simple. So if you solve it, this is going to be 240 MeV. 240 MeV. Okay, 240 MeV. So this is 240 MeV. So answer is Q 240 MeV. So in that case, energy is released because value of Q is positive, right? Exothermic reaction. So it is exothermic reaction. So which option is matching, guys? This is TIFR question. Option A is the correct option. I hope you have understood it. Okay. Next point. Next is next is threshold kinetic energy. Okay, threshold kinetic energy. Threshold kinetic energy, that is Q less equal to 0. When Q value is less equal to 0, that's threshold kinetic energy. Okay, so what is threshold kinetic energy? So this is a reaction, guys. Y X daughter, this is parent nuclei, this is projectile, plus that is equal to daughter nuclei, capital Y, plus that is ejected, right? Y. So this is at rest. This is at rest. Okay, this is projectile. Okay, this is at rest and this is projectile. So for this KTS, threshold kinetic energy, which is denoted by KTH. Okay, so KTS is going to be. Meanwhile, just let me check whether I'm audible or not. Then I'll proceed further. Okay. This one, and this is 120. Yes, I'm audible. So I'll proceed it further. Okay. So KTS is going to be equal to, that is minus Q value, okay, into 1 plus small mx upon capital Mx. Okay, so this one. So this is this very important formula. Kinetic energy equal to this one. Okay, so kinetic energy equal to this one minus Q 1 plus Mx plus M. This one. So this is minus Q 1 plus projectile upon mass of projectile upon and that mass of parent nucleus, right? So this is the answer. This is the KTS. Okay, this is threshold kinetic energy. Okay. Next is if there are more than two projectile, then what is going to happen? Okay, so there is A plus B is equal to C plus D, C plus D, C plus D plus E plus so on. Okay, so there are more than two projectile. If there are more than two projectile, okay, this is at rest. This is the case when there is only one projectile. Okay, now more than two projectile two projectile, more than two projectile, okay, more than two projectile, right? In that case, projectiles, okay, in that case, threshold kinetic energy, okay, that is going to be threshold kinetic energy, KTS, is going to be, we need to note down this formula as well. So minus Q into MA plus MB plus MC plus so on upon 2 MB, okay, an important formula. So KTS equal to this one, KTS equal to minus Q MA plus MB plus MC plus so on upon 2 MB, okay, but this is 2 into mass of that the mass of that parent nuclei, okay, or rest nuclei, rest mass of this P, okay. So this is the formula for if there are more than two projectiles, okay. This is important. And now next is total energy of particle is total energy more than two projectile created, right? This is projectile, guys. More than two projectile created, okay. This is projectile. So a total energy is going to be ETH. We'll write total energy by ETH, and that is going to be KTH plus MAC square. A is, that is rest mass of projectile, okay. This is projectile, guys. So this is important, okay. This one, total energy is KTH plus MAC square. MA is rest mass of the projectile, okay. Okay, guys, so this is the one. Okay, just give me 1 second, guys. There is camera is not working. Just let me check. Just give me 1 second, guys. Okay, camera is not working. Okay. Let me reconnect the camera, okay, guys, and then I'll proceed. Okay, so it's working now. So I'll proceed further. Okay. Well, so next is I'm going to solve one question. So question is 1p1 plus 1h3, that is titanium, right? This is 1h2 plus 1h2, okay, deuterium, right? It's titanium. Okay, so this is one. So number one is, okay, number one is, so you need to find out when proton is projectile. So this is projectile. Okay, when proton is projectile, when proton is projectile, find threshold kinetic energy. Okay, find k, kth. So this is given. Okay, simple guys. First we will find q value. Q value is q value. Q values we know that is uh, mass of, and we have been given, guys. Okay, this is, we have been given. This is given. Mass of proton is given, that is MP is given, that is 1.00785 AMU. Okay, and mass of deuterium is given, 1H2 is given, that is 2.014014102. Okay, and mass of 1S3 is given, titanium, right? 3.016049 AMU. So those are in AMU, atomic mass unit, right? So now we have to find Q value. Q value is Q equal to minus 1 upon 1 plus small mx upon capital Mx, right? So this is here projectile is proton, this is projectile, right? So this one, or I can write this one, Q equal to minus 1 plus mp, mass of proton, upon mass of 1h3, right? Mass of 1h3, this one. So I'll put the value and find the Q value. So Q value is going to be, Q is going to be minus, this is the KTH value, guys. First we need to find Q value. This is the value of KTH. KTH minus Q. First we will find value of Q. So Q value is going to be this one. Mass of reactant MP plus M1H3, mass of proton plus mass of titanium, right? Minus tritium, right? Minus mass of reactant minus mass of product. So that is 2m 1h2, right, into c square. So Q value is going to be, this MP value is 1.00785 7. So this is the value 1.007782 plus 3 point mass of titanium, right? 1s3. This is 3.016049 minus 2 into 2.014102, right? This one into c square into c square. So this value in MeV we will find out. This value is going to be minus 4.03 MeV. Minus 4.03 MeV. Okay. Minus 4.03 MeV. So now we'll find out KTH, right? KTH is like minus Q value is this minus minus plus, right? So minus minus plus means 4.03 into 1 plus this one, mass of proton upon mass of 1s3, right? So this is going to be 1.00785 upon 3.016049. Okay, so this value is going to be 5.3 MeV. Okay, this is the KTH, 5.3 MeV. Okay, and now second case, this is the first case, guys. Second case is, so now we have taken this one. Second case is when 1H3 is projectile. Okay, is projectile. This one, in this reaction, this is projectile. Okay, in that case, simple, the formula is going to be Q equal to my apologies, KTH is going to be equal to minus Q into 1 plus m mass of 1H3 upon mass of proton, right? So this is going to be minus minus 4, right? 4.03 into 1 plus 3.0160049 upon 1.007825. Okay, so this value is going to be 16.09 MeV. So KTH, so whichever will be a projectile, that will be in the numerator of this formula. Okay, so this is the answer, guys. Simple questions. Next question is, so there is one more question. Okay, the question is, P plus P equal to P plus P plus pi naught. Okay, so this is the, so we have been given MPC square, that is 938 MeV, and M pi C square, that is given 137 MeV. We need to find out KTH. KTH we need to find out. Okay, options are given: 284 MeV, option B is 394 MeV, option C is 340 MeV, okay, and option D is 240 MeV. Okay, so this is the question, and we have been given this, and we have to find KTH, right? So this is the case given. Okay, So in this case, so there are more projectiles. So KTH is going to be, value of KTH is going to be this one, minus Q into MP plus MP plus MP plus MP plus M pi upon 2 MP. Okay, this is one, because P is the projectile here and P is the rest. This is rest. Okay, so value of this KTH is going to be Q value is also given, right? Okay, Q value is given, that is minus 137 MeV. Q is given. So KTH is going to be minus minus plus, so 137 into MP, this is 1 plus 1 plus 1 plus 1, 4 times 1, right? Plus M pi upon mass of proton is 1, okay, 2 into MP. Right, now what we are going to do is, this is going to be 137 4 plus M pi upon 2 into MP, and we'll multiply this by C square and C square, right? So now we have, because why we are doing that, because we have been given MP square value is this and M pi square value is this, right? So then we'll put the value here. Okay, this is going to be 137 into 4 plus M pi C square upon 2 into MP. MP value is given, MP C square, right? MP C square value we have been given 938. This is MP C square, so 938. If you solve it, this value is going to be equal to KTH 284 MeV. 284 MeV. Okay, this is the answer, guys. Okay, next is guys, radioactivity. Okay, radioactivity. Radioactivity. So radioactivity, we need to understand. I'll write some points. Due to imbalancing of forces, due to imbalancing, of forces, due to imbalancing of forces inside the imbalancing of the forces inside the nucleus, the forces inside the nucleus are imbalanced. Okay, not balanced. Okay, nucleus, and due to short range of nuclear forces, due to short range of short range of short range of nuclear forces, nucleus simultaneously, my apologies, spontaneously disintegrates into their into their stable nuclei. Okay, so this is due to imbalancing of forces inside the nucleus, and due to short range forces, short range forces, due to of nuclear short range of nuclear forces. That's correct. Short range of nuclear forces, nucleus spontaneously disintegrates into their stable nuclei. Okay, that is radioactivity. And next point is the substance, the substances, the substances achieve, the substances achieve stability, substances achieve stability by disintegrating, substances achieve stability by disintegrating, and excess energy is emitted, and excess excess energy excess energy is emitted, excess energy is emitted in form of, in form of radioactive, in form of radioactive radiation. Okay, so the substances achieve stability after disintegration by disintegrating, and excess energy is emitted in the form of radioactive radiation. Okay, this one. Next is so this is a parent nucleus. Okay, parent parent nucleus. Okay, this disintegrates and forms daughter nuclei, forms daughter nuclei. Okay, after disintegration, and that is stable nuclei. Okay, and now we need to understand DPS. What is DPS? DPS is disintegration per second. Okay, DPS means disintegration. DPS means disintegration DPS means disintegration DPS means disintegration per second. So disintegration in second is DPS. Okay, that is called DPS, disintegration per second. And this is called disintegration per second. This is called activity. This is called activity this is called activity of radioactive sample. Okay, of a radioactive radioactive sample. Okay, so the disintegration per second is called activity of radioactive sample. Okay, activity of radioactive sample. Okay, so activity is here, activity is denoted by C, and that is equal to mod of dN upon dt. Disintegration per second, mod of dN upon dt. Mod of dN upon dt. okay, mod of dn upon dt. Or we can write activity AC equal to minus dn upon dt. So we have taken just mod, okay, so that's why. So minus the other actual value activity is dn upon dt, okay. And the the unit is this becquerel, guys. Becquerel, unit of activity is becquerel, that is becquerel. Becquerel. And one disintegration per second dps, disintegration per second, one dps equal to 1 becquerel, okay. This is denoted by bq, denoted by bq, denoted by bq, okay. And 1 ci, that is curie, 1 ci equal to 3.7 into 10 to the power minus 10 disintegration per second, disintegration per second, okay. Ci is curie, guys. And similarly 1 Rutherford Ru is equal to 10 to the power 6 disintegration per second dps, okay. So this is Rutherford, this is Curie, guys. Curie, okay, this is, and this is Rutherford, okay. Next point is next point is Ra, that is radioactivity, is purely a nuclear phenomenon, okay. A nuclear phenomenon, purely nuclear phenomena, okay. And second, Ra means radioactivity, okay. So radioactivity is independent of electronic configuration, electronic configuration, okay. So radioactive is independent of electronic configuration. Next is in different isotopes, in different isotopes, different isotopes, the chemical properties, the property chemical properties chemical properties of radioactive chemical properties of radioactive and non-radioactive non-radioactive isotopes 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 remain same, okay, remains same. Okay, in different isotopes, the chemical properties of radioactive and non-radioactive isotopes remain same. So radioactive and non, if they have they are isotopes, one is radioactive and another is non-radioactive, their chemical property will be same. Okay. Next point is for radioactive. Radioactive is a random process. Okay, radioactive is a random process. Radioactive is a random process. Okay. Next point. Okay. Next is, just let me check whether I'm audible or not. Nucleus simultaneously. Yes, I'm audible. I'll proceed further. So radioactivity. So now radioactivity law. Okay, radioactivity decay law. Radioactivity, radioactivity decay law. Decay law. Radioactivity decay law. Okay. So AC, that radioactivity is equal to dN upon dt. This we know, mod of dN upon dt. This we know. And also guys, AC, that is activity, is proportional to n, number of initial sample. Okay, n. So n. So that is number of nucleon, right? So initially, 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 that initially at initially number of nucleons are number of nucleons. Okay, initially at t equal to 0, there are n0 that number of nucleons. Okay, radioactive, and at any instant, at any instant t. Okay, n is n is remaining nuclei. Okay, this is number of nuclei. Initially there are n0 number of nuclei. Okay, n is at any instant t, n is remaining nuclei, remaining nuclei after decay. Okay, so at any instant t there are n nuclei are remained. Okay, that is at t equal to t, at time, at t equal to t. Okay, so initially the number of nuclei are n0, and after time t there are remaining nuclei are n. Okay, so this means, therefore, number of decayed nuclei, number of decayed number of decayed nuclei will be n minus n0 minus n. Okay, because n is the number of remaining nuclei after decay, right? N0 is the initial number of nuclei, right? So the number of decayed nuclei are going to be n0 minus n, right? So n0 minus, and here we can see, because activity is proportional to n, right? Our activity formula is d upon dn. This is activity, right? Proportional to n, or we can write dn upon dt is proportional to n, or we can write dn upon n minus dn upon n equal to lambda n. Okay, where lambda is decay constant. Okay, lambda n. Okay, so lambda is decay constant. lambda is decay constant. Okay, so this is going to be, now what we can do is we can write dn upon n equal to minus lambda n, and will nt, this is dt, right? Dt, so this is lambda n dt. Lambda dt, sorry, lambda dt, because n will, we have taken n in left hand side, right? Lambda n dt, will integrate it. To integrate it, this is t, right? From t equal to 0 to t, and here n equal to n0 to n, remaining nuclei, right? N. So we'll integrate it. So this is going to be, if we integrate it, so this is going to be ln n0 upon n. This is ln n0 upon n, right? Ln n0 upon n, ln n upon n0. My apology. Ln n upon n0, that is going to be equal to minus lambda t after integration 0 to t, right? So from here, n upon n0 is going to be equal to e to the power minus lambda t. Okay, so n value is going to be n0 e to the power minus lambda t. So this is important formula, guys. Okay, you need to note down and memorize it. This is, n is number of active nuclei. Okay, number of active nuclei, number of active nuclei, or this n is n0 is number of initial nuclei. Okay, number of initial nuclei. Okay, this is important formula, guys. You need to note down and memorize it. Next is decay rate. Okay, decay rate. Decay rate is denoted by lambda, and that is lambda equal to activity upon n. Okay, that is decay rate, or we can write 1 upon n mod dn upon dt. Activity formula is mod dn upon dt, right? So this is the decay, or this one. So this is the formula. Okay, lambda equal to, these are important formula. So, or we can write lambda equal to, the unit is lambda equal to disintegration per second upon nuclei, right? That is unit of decay rate. Okay, so decay rate is activity upon n, or 1 upon n mod dn upon dt. Okay, now half life. So this is half life. Half life of a radioactive substance. Half life of a radioactive substance. Okay, so so suppose half life, suppose at t equal to 0 there are n0 nuclei. Okay, at t equal to 0 there are n0 nuclei, and at t equal to tau half, that is half time, right? At t equal to tau half, the nuclei remains half of its initial nuclei, that is n0 by 2. Okay, so that is the time in which half of the total nuclei, in any sample is decayed. Okay, the time in which half of the total nuclei in any sample is decays, half of its total nuclei. Okay, that is called half life of radioactive substance. Okay, or so mathematically we can write, since we have formula n equal to n naught e to the power minus lambda t. I have just derived it, right? This one, e to the power minus this formula, right? So this from here at if half lifetime is going to be at time t tau half, it is going to be this is this is this is going to be this is going to be n0 by 2, half of the initial nuclei, and this is n0 e to the power minus lambda tau half, right? So n0 n0 will get cancelled, right? So from here 1 upon 2 is going to be equal to e to the power minus tau minus lambda e to the power minus lambda tau half. Okay, so from here we can write e to the power lambda tau half is going to be equal to 2, and or we can write lambda tau half is going to be equal to 2 upon ln2. This is ln2. We have used log property, right? So from here tau half value, that is tau half value is going to be this one, ln2 upon lambda, right? Or we can write ln2 value is 0.693 upon lambda. This is the very important formula for half life of the radioactive substance. Okay, so tau half equal to 0.693 upon lambda. Okay, now mean half lifetime. Okay, next is mean lifetime of a Ra element. Mean lifetime of a Ra element. Okay, so mean lifetime of a radioactive element. So what is mean lifetime, guys? So what mean lifetime is denoted by Tm, and that is 1 upon lambda, guys. So very important. Tm equal to 1 upon lambda. So decay rate, we can write decay rate is a constant decay rate is a constant for each element. Decay rate is constant for each element. This is decay rate, lambda is decay rate, right? So mean lifetime is also constant, okay, this one. Next is radioactive series. Radioactive series. So this is important one, guys. So like parent nuclei, I'm writing parent nuclei with P. Okay, parent nuclei of P, and I will write parent nuclei will become daughter nuclei, right? And then daughter nuclei will become sub daughter nuclei. Okay, and then it will become stable and product. Stable and product. Okay, stable and product. So here I will write So for example, like we have A1, okay, that is it became A2, then this became A3, okay, this became A4, so on, An, okay. So lambda constant is lambda 1, lambda 2, lambda 3, and so on. These are decay rate, okay. So here this is important, you need to note lambda 1 greater equal to lambda 2 greater equal to lambda 3, decay rate, okay. So lambda 1 greater equal to lambda 2 greater equal to lambda 3. So these are daughter parent nuclei, then daughter nuclei, then sub daughter nuclei, then product, okay. So now I'm going to explain very important thing, okay. So that is radioactive series, okay, radioactive series. So that is mass number, okay, series, parent nuclei, and stable and product, stable and product, stable and product, okay.